This is Electronic Devices and Circuits, Module 2. In this module, we will look into these topics: mobility, conductivity, drift diffusion equations, generation and recombination, lifetime and excess carriers. In this lecture, we will look into mobility and conductivity. First, let us consider a semiconductor. Having a semiconductor here, semiconductor bar, and it is having two leads at its two ends. Let us consider two cases. First case, the semiconductor is in equilibrium. So what is meant by equilibrium? There is no external excitation on the semiconductor, no energy applied on the semiconductor other than temperature. So equilibrium means no external excitation. So what happens under this case? You know that the applied electric field in this case will be zero. We are not applying any potential difference across the semiconductor, so the applied electric field is zero. But one thing we need to remember here, even when there is no external excitation, even when the applied electric field is zero, the carriers will be having a random motion inside the semiconductor. Carriers inside the semiconductor will be having random motion. This is because of the thermal energy which is there, because of the room temperature. They have this thermal energy, and because of this they will be undergoing a random motion. But this random motion won't contribute for current or any conduction, because the net flux in this case is equal to zero, hence they do not contribute for conduction. Let us take a second case. In this case, we apply an electric field. Some electric field we apply. How do we apply an electric field? We are having two leads here. Apply a potential difference across this semiconductor so that there will be an electric field. This is the electric field inside this. So what happens because of the applied electric field? The carriers inside the semiconductor will have a force, will experience a force. Carriers will experience a force which is given by Q into E, where Q is the charge of the carriers and E is the applied electric field. So there is always a random motion of carriers inside the semiconductor. Even when it is in equilibrium or when an applied electric field, random motion will still be there. So here, in addition to this random motion, because of this electric field, there is a directed motion. So because of this, there is an additional velocity. It attains an additional velocity, which is known as drift velocity. So here it is a directed motion which is imposed on a random motion. This directed motion is because of this applied electric field, and hence the carriers experience a force and gain an additional velocity which is known as the drift velocity. The expression for drift velocity is V drift is equal to mu into E. We know that E is the applied electric field. And what is mu? Mu is the mobility. You have to remember this expression. Mu is the mobility, and what does mu signify? It signifies the ease with which the carriers can move. So higher the mobility, higher will be the drift velocity. So what are the units of mu? You can directly find out from here, from this expression. You can see that mu will be V drift by electric field. So V drift will express as centimeters per second, and electric field will express as volts per centimeter. So the units of mobility will be centimeter squared per volt second. So we are having two types of charge carriers inside the semiconductor, that is electrons and holes. So both will have different mobilities. So mu of n and mu of p. Mu of n means mobility of electrons, and mu p means mobility of holes. Mu n will be greater than mu p, and if you take for silicon, mu n will be approximately 2.5 times mu p. 2.5 to 3 times you can take sometimes. So this is worth remembering. This is a very important design consideration in CMOS circuits, because when you are having a CMOS circuit, you will have NMOS and PMOS transistors, and if you have to balance the current through NMOS and PMOS, while designing you have to take the W by L ratio accordingly. So this we will see later. While designing the parameters of the transistor, you have to take this into consideration. Next we will look at an important current component in a semiconductor, which is known as drift current. We will look into drift current density. Which is denoted by J drift. So what is this drift current density? How this is coming into effect is, we know that carriers are having this additional velocity V drift. Because of this additional velocity, they have a flux. There is a flux of carriers, and because of this flux, there is this drift current. So this drift current is given by charge times concentration of concentration of carriers into the drift velocity. So I'll say again, like, why this drift current is coming. This is because of the drift velocity. Because of the drift velocity, there is a flux which is being contributed, and hence we are having an additional hence we are having a current which is known as drift current. So if you take for electrons, it will be Q times N times V drift, and if you take for holes, it is Q times P times V drift. So what is N? N is the concentration of electrons, which is expressed in per centimeter cube. P is the concentration of holes in the semiconductor. This is also expressed in per centimeter cube. So you can write drift velocity in terms of mu and electric field, Q times N times mu N times E. Here it will be Q times P times mu P times E, and the total drift current density will be the sum of these two terms. So we can see here drift current will depend on charge times concentration of carriers. Higher the concentration of carriers, higher will be the drift current. Higher the mobility and electric field, higher will be the drift current. It depends on concentration and electric field. This is the total drift current density. To get the drift current from here, this is current density. To get the drift current, you just have to multiply this drift current density with the area of cross section where the current is flowing. So this is an important expression which you should remember. This will write in another way. J drift Q times N times mu N plus Q times P times mu P. This whole thing will multiply with electric field. This electric field term we are taking it outside. So this is one popular expression which we know. This term is known as sigma. What is sigma? Sigma is the conductivity. So this we are expressing it as sigma into E. Sigma is the conductivity which is given by Q times N times mu N plus Q times P times mu P. So this also you have to remember. So based on this, I'll give you two assignment questions. So A 2.1, try to find out the units of drift current density. It is straightforward from here. Just substitute the units for all these quantities. You know, for Q it is coulombs, N it is per centimeter cube, mu N it is centimeter squared per volt second, which we have seen in the previous slide. And for electric field it is volts per centimeter. To try to find out the units of drift current density. And assignment 2.2, try to find out the units of sigma, the conductivity, and try to see how sigma is represented. What are the standard units used for sigma when we are seeing it for semiconductors? When we are dealing in semiconductor theory, you see what is the standard unit, standard way in which sigma is represented. Please solve these two assignment questions. Next we will see how mobility varies with different parameters. Mobility with doping. First we will see mobility with doping. You have to remember here one thing. This is total doping in the semiconductor. So we know that mobility implies it signifies the ease with which the carriers can move. So what happens when the doping is increased? When doping is increased, you will have more number of impurity atoms or ions. Impurity ions will be there. Because of this, there will be more scattering and more collision of the carriers with these impurity ions which are there. So if there is more scattering, the ease with which the carriers can move will reduce. So higher the concentration of dopant atoms, the mobility will reduce because the ease with which the carriers can move will decrease. So hence we expect a curve like this. It will decrease with increasing doping concentration. This you can say this is the curve for mu N, and the curve for mu P will be similar, but the magnitude of mu P itself is less. It's around like 1 by 2.5 times mu N. So you can expect a curve like this. So mu N, if you take for silicon, mu N will be around 1350 centimeter squared per volt second. This is the highest value for electrons, highest mobility for electrons in silicon. And for holes, this will be around, it will start around 450 centimeter squared per volt second. It is good to remember these values, good to know the range of mobilities, because it might help you in solving problems or in designing some CMOS circuits. So this mobility with doping we saw now. There is one more variation of mobility. This is with temperature. This I will give you as an assignment question, A2.3. So you find out how mobility varies with temperature. So this you can find in any standard semiconductor textbook. Just spend some time on it and see how mobility is varying with temperature, whether it is increasing or decreasing, and try to explain the regions. There will be two regions. Try to explain the two regions, why it is either increasing or decreasing with temperature. Please solve this assignment.